Hello. Hello. Good afternoon, sir.
Good afternoon.
Can you start the second question, sir?
Yes, yes.
Okay, sir. Thank you.
Yeah. On a Linux platform. So this is simple. It's not much difficult to install OpenMPI on a Linux platform. So this is a PDF. If you Google out, just OpenMP install PDF. So you will get this first link on the Google and simply download it and follow this step one by one, and you can get OpenMP installed. So as I already told you in the morning that OpenMP is freely available with GCC, but OpenMPI we have to install. Okay, we have to install. There it is, and all these softwares are freely available. So what are the simple steps? Just we'll go through at a glance. So you will know what are the steps that you have to follow. So you have to create one temporary directory for compiling OpenMPI, so that you can create in the home directory of a Linux under local, under source. Okay, it can be anything. You can create any directory. There is not an issue. So, but this is the standard one which you can follow. So, the create a directory under home, local, and source. Download the latest version of OpenMPI which is available on this website. Okay, this is very older one, 1.44, but now it is the latest are available, so that you can download from this website. The moment you get this, what you have to do, you have to move that entire downloaded file, which is this BZ, to the directory which you have created. So just we are moving the download directory to the source directory in which we have to put that particular what we can say file. Fine. Then you just go into that directory where you are having your OpenMP file. This is this particular software file. So you are in that, and then you use this tar. So by using tar command, all the things are get extracted from the file, which is OpenMPI with some extension with tar.bz2. Now then, fifth step, just you go inside. So once you will extract everything from this particular zip file, so it will create one folder where MP-1.7.8 or something, whichever is the latest. So just go in that particular directory. The moment you will go in that directory, just you have to perform this sixth step, just /config. Okay, and then you give the prefix path of home opt OpenMPI. So this prefix path will get installed. So whatever this particular directory which you are giving, this inside this directory, all the binary files, all the executables of OpenMPI, all the header files or the library files or the executable files will be available after the installation. So you are making that. Then here we are using, you have to make a make all and make install. So whenever you are doing this, just you do as a root user. Just you use the sudo before that. So if you use a sudo before that, so it will be an administrative command. Okay, and with that administrative power, you are able to do this all. So sudo make all, you do this. It will take a time. Okay, so approximately 20 to 30 minutes it takes to install everything, because it is very big library, because it is a message passing interface. So whatever the different programming language through which we can have the communication, those all integration need to be there. Then make install, and after make install, the things will be done. So this will be installed OpenMPI in your home directory in the subfolder called as this. So you can speed up the this particular operation by doing this, but don't go for this. Just follow this. Let it take the time, no problem. Then remove the temporary directory. If you require, you can go for the 7th step. If you don't go for this. But the last step, this is very important. This will help you to set the path for the library file, that is the bin file, and to set the path for library file. So there are two folders, bin folder and library folder. This path we need to set. So in bin folder we will have all the executables like compilers, and in library files all the header files that are needed. So just you copy this particular first command on the terminal and you paste it, and you copy the second command on the terminal and paste it, so that these two paths, okay, these two paths will get exported in the file called as bash rc, and then onwards your program, you can able to execute the program. Okay, so this is 7 step you have to follow. They are not complicated, just follow as it is given in the PDF, and then it is available for you to work on OpenMPI. Okay, so I stop here for this installation. Just you go through and you can get the OpenMPI ready for your machine. Fine. Now moving further, so we will start the today's session. So it is based on OpenMPI. So OpenMPI is an open message passing interface. Irrespective of any programming language, the OpenMPI is applicable. The job of OpenMPI is just to pass the messages, and by passing these messages, you can able to achieve the task. So that we will see in this class. Fine. So what exactly message passing interface? So a parallel programming paradigm widely used on parallel computer. Okay, so we are having lots of computing infrastructure. Simple example I want to give you, your lab. Okay, in every institute we are having so many computer labs. So in the labs you are having so many machines. Yes. So if you take one machine and if you take another machine, so that can be a one distributed environment. Okay, they are connected to LAN. Okay, but they are independent machine, just connected to the LAN. So here you can make this all machine to be work, okay, as a parallel computing infrastructure. So if one machine want to communicate with the another machine for solving a particular problem, so here you can use the message passing interface. Okay, so for that what you have to do, you have to install OpenMPI on all the machines. You have to create the user on that machine with the same name, same password. Okay, and then by using their IP addresses and by using their username and password, you can make them connected in the network, and you can utilize message passing interface to just exchange the data, exchange the messages, and those machines independently work on certain data with respect to certain program. Okay, so that we see. So here with the online constraint, we are not able to exploit how that can be done in a particular lab, but we can exploit on a particular machine, the laptop on which I am demonstrating this particular PPTs. Okay, so there also we can have the OpenMPI implementation, right? So what are the infrastructure that are available for message passing interface? The first one is a scalable parallel computer. Like the people keep on adding the computers in the particular computing facility. So there also we require a message passing interface. There can be a network of workstation. You can have so many workstations in their network, irrespective of their geographical locations. Okay, irrespective of their geographical location. So there also we can use a message passing interface to exchange the messages and to distribute the work with respect to the data on which independent machine need to work. Fine. So this is an example which will help you to understand how that message passing infrastructure is all about. Fine. So you will have some communication network, okay, so which is an internet through which, or it is a communication medium through which the machines can communicate. Fine. Now, so this whatever this square you are able to see, this is a processor. Okay, this is one processor, another processor, and this processor will have some memory. This is a memory. So in this memory, the data will be get accommodated. Okay, so each and every machine or each and every processor, you can say, rather saying a machine, I say processor. So processor can be a node, processor can be a machine, processor can be a processor on the same machine. Fine. And here, this is the program which we want to compute. Okay, this program we want to execute in parallel. So the program will be made available to all the processors. They are connected in a communication network, and through this communication network they can exchange the message. And each and every processor over here is having its own data. Okay, is having its own data. So here to execute this work, this particular program, I want to execute this program. Yes, this program is having, this is the data. So this data, how that can be partitioned and how that can be sent to this, that all thing will be done by message passing interface. And moreover, whatever the processes that are available at this instance, they may have some different compute capability. Their RAM will be different, their CPU speed may be different, and all other things may be different. But they may take part in the computation of this program which we want to execute in parallel. Okay, so we'll see in more detail. So this is the infrastructure required for message passing interface. So this can be in a distributed environment, or this can be in a shared environment. Shared environment means a laptop, a desktop in which you are working. Because nowadays desktops and laptops are having more than one processor. So there also we can create the message passing environment in which we can exchange the messages. Fine. So moving further. So the memory model for parallel programming. So already one model we have explored in the morning, which is a shared memory model. So there are three different types of memory model. The shared memory, where the memory is available on a machine, and that memory will be shared by number of cores, number of processors available on same chip, okay, or same motherboard. Distributed means the machines are, or the processors or the computing machines, they are available at different locations, and they are connected via communication medium. So there the machine will have their own memory. The computing machine will have their own memory. So that is one infrastructure. And another one is a hybrid, which is a combination of this and this. Okay, combination of this and this, where there is a shared memory will be shared by some processor, and there is a distributed memory. So we will see in detail how these particular architectures are look like. Then it will be easy for us to understand the applicability of OpenMP in different memory environment. So see, this is the architecture. Okay, the shared memory model is like this. So this is your desktop or laptop having a memory, and there are so many processors. See, there are so many processors connected. So they are having there, they can, these all processors can share this memory. Moreover, if, shared memory. And then there that shared memory also called as UMA, Unified Memory Access, which is applicable for OpenMP. This is also another example where the one particular machine is a gate connected to another machine, okay, in a network connection, where if you see, for this machine this is the memory available, for this machine this is the memory. So this is exactly distributed over here. But if you will see one machine at this particular point, so this is available in a shared memory model, where these CPUs can access this memory. But if you consider this is a one independent memory machine, and this is another independent machine, so where it is having its own memory and it is having its own memory. So when something need to be exchanged, okay, some data which we want from this processor, and that need to be get processed at this particular point, so here we can exchange the data through MPI, through message passing interface. So moving further, this is exactly called as distributed memory model. So in a distributed memory model, you will have only one processor. But nowadays, this is not possible. Nowadays, we will going to have this architecture. Okay, we will going to have this architecture. That is the old one, where there is only one CPU and one memory. But nowadays, the architecture is something like this, where we are having a many processor which will have this particular memory. So now this is exactly the distributed memory model where these all machines are connected to the network. So when I say network, that means they will be available at different geographical locations. Okay, and through this network we can assign the task, we can send the task, and we can send the data on which this machine will independently work. Moreover, whatever the machines they will connected through this network, they will have different compute capabilities. That means different memory size, different CPU speed, and all other things. Fine. Now moving further, the hybrid. Okay, moving further, it is the hybrid model. So hybrid model means it is a combination that what we have seen. Okay, so whatever nowadays which you get, everything you will get hybrid. Okay, it is hybridized nowadays. So the machine is there which may have a 4 CPU, 10 CPU, the another machine which may have a 2 CPU, 20 CPU, another like this, likewise, and they will have their own memory and they are connected. Okay, so this is the giving a feel of every machine is having its own memory, and if you see closely to one machine, then it is a shared. Okay, so closely when we look, it is a shared, but independently when we see, it is a distributed memory model. So this memory size, here it can be a 8 GB, here it can be a 16 GB, here it can be a 32, here it can be a 4 GB likewise. Fine. So this is the hybrid where distributed we can able to see here, here and here, and when you want to see shared, so just we have to closely look the number of processor they can share one particular memory. Fine. So these are the memory models which we have. So based on this memory model, we can able to use different programming languages exclusively for writing parallel program. So what is the goal of OpenMP? What exactly OpenMP made for? So the OpenMP is developed widely used standard for writing message passing interface. So whenever message passing kind of interface you want to use, either in shared memory architecture or a distributed memory or hybrid, so most of the widely used standard is OpenMP. Okay, so it is widely accepted and it supports all the types of programming languages like OpenMP, MPI, CUDA, Java, Python, all. It supports all the kinds of programming language because the job of this API, this is itself a kind of an application program interface. Okay, where what it does, it just a particular method how the data will be sent from one particular place to another. That's all, nothing else, just for message sharing. Like we are having a WhatsApp. What we do from the WhatsApp, just we send the message. We don't do any computation. So that is done by this. And when the data will reach to the respective end and the program will reach to the respective end, that end will do the computation. Okay, that's why it is a widely accepted standard. Next, the interface should establish a practical, portable, efficient and flexible standard for message passing. That is another goal of MPI, that practical implementation has to be there. It has to be portable, efficient and flexible as per the various programming language in which we want to use the MPI. And the next one is design and application programming interface. So the ultimate goal of this OpenMP is it has to be an API kind of stuff so that can be utilized. So for parallel compiler or various libraries. So if it is an API, so we can easily integrate and we can utilize. Yes. So nowadays if you are using a Python, so in Python we are getting a lots of API. Simply we integrate that API in Python and we can exploit that API and we can utilize that. So that is the objective of this OpenMPI. That is the major goal. With respect to MPI, what is allowed and what is not allowed. Okay. So it allows efficient, reliable communication interface implementation used in heterogeneous environment. Heterogeneous means whatever the platform, that is the hardware which you use, we are not expecting that the configuration of that hardware will be same. It will be different. So that kind of environment is supported by the OpenMPI, that to be efficiently. What it avoids, memory to memory copy it avoids. From one memory to another memory copy is avoided. Overlap of computation and communication it avoids. Okay, and offload of communication to processor. So memory to memory copy, it is avoided by the OpenMPI, overlap of computation and communication. When communication is going on, that time you cannot do the computation, because if the data for which the data which is required for computation, it is not supplied, okay, so computation will not going to start. So that is that particular strategy. Overall, overlap of computation and communication has to be avoided, and offload of communication co-processors. So it cannot offload when there is a communication between co-processor and processor. So what is a processor? Processor means your central processing unit, and co-processor means an additional processor for which which is utilized to perform some exclusive tasks like a GPU. GPU is there, FPGA is there, these are the co-processors, okay. So co-processor and processor communication we cannot offload. The communication has to be there towards to send the data. Fine. Now, in what way we can compile the OpenMPI program and in what way we can run. So, already I have told how to install. So, by following that steps, you can install the OpenMPI program, OpenMPI in your machine. So this header file you have to add. For compilation you have to use MPICC, that is MPICC stands for C compiler. Then the program name .c. Then this is the object file which we are creating. And for running you have to use MPI run. MPICC only for compilation. MPI run is only to run the program in number of instances. So see how it is. MPI run -NP. So NP stands for number of processes, and this 4 indicates it will create 4 processes. Okay, and these 4 processes will be scheduled on the 4 cores if available at that point. And then here the executable file. So this is the executable file. Okay, this is the executable. So this is the way to run the program, and this is the way to compile the program. Now moving further, what exactly the massive passing paradigm, how that is exactly done, okay. So if we consider the sequential program paradigm, okay, so in sequential program paradigm what you have? You will have a processor or a process, okay, and that processor or process will require a kind of memory or will have a memory. So a processor may run many processes. Yes, it is possible. But if it is a sequential, so first of all it will run one process. Once it is finished, it will jump to the another process. So in that way, time multiplexing will take place, and the number of processes are get executed. So that is the sequential program paradigm. A program is there and data is there, it is get executed at a time, and then next program and next data likewise. But in message passing programming paradigm, we are having a communication network. That means through this network, these all processes or processors are connected. Okay, they are having their own memory and they can execute a particular program with respect to different data. Okay, though it is written data, but this will be a data 1, this will be a data 2, data 3, and they will go to execute the same program. So distributed memory we are able to achieve here, and parallel processor we are able to achieve here. Fine. So this is the way the message passing paradigm helps us. Okay. So we will move further. So a process is a program performing a task on a processor. So that is already known to you. Fine. You are already known. It is a process, is a program performing a task. So particular task is given and that task is get executed on a particular data value. Yeah. So each processor or process is a message passing program. Okay. So whatever they will going to execute, it is a message passing program, runs an instance or a copy of a program. So that we have seen here. Like whenever you are running MPI program, what we do, we specify how many processes. So this many processes. So how many processes? 4. So it will create a 4 instances of same program, and that will given to the number of different processors, and whatever will be the part of that processor, that is getting executed. Okay, so entire instance of that program is supplied to different processors. So that is the meaning of this sentence. Each processor or process in a message passing program runs an instance or a copy of entire program. So what exactly, how we can write that program? So it can be written in conventional sequential language like a C, C++ or Fortran easily. Typically a single program operating of multiple. So you have to write only one program and it will operate on multiple data values. Okay, let's say an example of matrix addition. So you are having the matrix size is 1024 by 1024. Yes. So what we can do, we can divide that entire data into small chunks, and that particular chunks can be given to different processors. The variable of each subprogram may have, whatever the variables of each subprogram may have same name. Okay, this is the restriction. If there are different names, so there is a conflict towards to solve the program. Okay, towards we execute that program. So they must have same name, but a different location, that is in distributed memory, and a different data. That is, all variables are local to a process. So whenever these variables will go to a particular processes, so that time they are local and they will execute locally at that particular point with the supplied amount of data. And then communication via special send and receive routine. So then there will be a communication. So there will be a send and there will be a receive. So send will be done by one processor and receive will be done by another processor. So whenever there is a message passing, there is a pair. Send will be from one process and receive will be from another process. Let's say another process want to send, so the next process has to receive. So whenever there is a message passing, this pair has to be there, send and receive. Send at one end, receive at the other end for the same data value. And that will be done under this particular infrastructure. Now moving further, how data and work are getting distributed in OpenMPI, because that is the important one. We have to tell what is the task a machine has to do and what is that particular data on which the computation need to take place. Fine. So that can be, with this particular example we will see here. So to communicate together MPI processes need identifier. So whenever we want to have a communication, so every process or every processor must have some identifying number. Okay, and that identifying number is called as a rank. So every process or every processor will have a rank, and the rank will start from 0, 1 to n minus 1. Okay, so if you are having total 10 processors, so the rank of first process will be 0 and the rank of last process will be 9, starting from 0 to 9. All distribution decisions are based on the rank. Okay, so which will be the rank handling what kind of data, that will be decided. So this is very important factor. So without which it is not possible to send the data or to send the work. So which process works on which data, that can be easily determined by the rank. So see, this is your process. Okay, this process is having a particular program to get computed, and the rank of the process is determined over here. So rank 0, then rank 1, rank 0 will have some data 1, rank 1 will have some data 2, rank 2 will have some data 3, likewise. Okay, and now our rank 0 is the master what you can say, master process, which will going to initiate the activities. Okay, and it may or may not take part in the computation. It may initiate and it will wait to receive all the results. Okay, but in OpenMP what we have seen, when we create a number of threads, okay, so master thread also involves in the computation. But in OpenMPI it is not necessary that master process will going to take part in the computation. It may or may not, because totally it is programmer based. Whatever the program you will write for master and whatever the program you will write for the remaining process, which you can say slave, that according to that things will going to happen. Fine. So moving further, in what way the message passing will exactly happen? Okay, so what is the message passing? Messages are the packets, just the packets which we need to deliver. So messages are packets of data moving between sub-program. Okay, so there will be a program, and in between that program there is a sub-program. So the data will be moved. Fine. Necessary information of the message passing systems are this. This many information has to be there when we are constructing a packet which we need to transfer from one processor to another processor or one process to another process. So what it requires? Sending process it requires sending process and the receiving process, that is the rank of the process. So either it will be 0 or 1 or it will be some another one. Then a source location, the destination location is required. What is the source location? What is the destination location? Then what is the source data type and destination data type? So source data type means a data value. So you want to send integer data, you want to send character data. So that need to get specified at the source point and as well as at the destination point. Moreover, size of the data need to be specified. How much in byte? 100 bytes, 200 byte, likewise, both at the source point and both at the destination point. So these are the information required. So then once that information is framed in this packet, the packet will move from one process through communication channel to another process. And then here this packet will be get retrieved, and based on the information is available, this particular process will perform the task. Okay, so these are the important information that are required at this point. Moving further, how that access can be there, because without accessing the packets, I cannot retrieve the information. Why? Yes, so a subprogram need to be connected to a message passing system. That is the first and foremost condition. Whatever the program which we want to execute, that must connected to message passing system. So how that message passing system is, that we have to see. So the regular message passing system is similar to phone line, mailbox and etc. So in phone line what we have, one phone is connected to the communication channel to the particular center, and through that particular center another phone line is there. So if that center is not available through which all the communication takes place, so we are not able to exchange the message, which is same in phone line. And similarly in mailbox also, we have to have the mailbox on a particular subscriber, and through that subscriber we can send the message. So if there is a no mail server, I cannot send. If there is a no infrastructure for phone line, I cannot send. So that infrastructure is called as message passing system. Okay, so what we have to do, we have to create the message passing system. Okay, and that simply we can do by using MPI libraries. That's all, nothing else. We don't have to set up anything, we don't have to install any exclusive software. Just by using message passing libraries, we can create that infrastructure. Okay, so how? So that is MPI. So program must be linked with an MPI library. So your program must have an appropriate MPI libraries, and program must be started with the MPI startup tool. So your program must start, and then once it starts, it need to get integrated to the MPI, that is message passing interface infrastructure, and then only you can start exchanging the messages. So to understand this, suppose I want to call to some person, but I don't have a SIM card. So how I can contact? Without SIM card, I cannot contact. So SIM card I have to purchase, and that SIM card will be belongs to a particular vendor. That vendor is providing me the communication infrastructure. So once I get connected to that communication infrastructure, then only it is possible for me to have the communication. Same thing is applicable here as well. So there are different types of communication, like a point-to-point communication, and there are other. So it is the simplest form where one process send a message to another process. That's all. Different types of point-to-point communications are synchronous send, okay, or a buffered, which is called as a asynchronous send. So when you want to send the message from one process to another process, point-to-point communication is utilized, where the either of synchronous send or asynchronous send. Synchronous send says that when you are sending the data, till the data is reached, nothing has to be happen. Means no other process are allowed to do anything. Okay? No, means on that particular processor you can't do anything, but it is asynchronous. Asynchronous means what? Just you send the message, whether you get an acknowledgement or not, you don't bother for that. So for synchronous send, you are waiting for the acknowledgement. Once you get an acknowledgement, the process will go further. In asynchronous, you send the message and you involve yourself to perform some other operations. You are not bothering whether it is reached or not. So you are just believing that MPI infrastructure will deliver that message. So that we can understand by using this particular figure, which is a synchronous send. So in a synchronous send, the sender will send the message, okay? So the message will go through this communication channel. It will go to deliver it here. The moment the message is delivered at this end, it will go to give you the beep or the OK signal. So what is happening in synchronous? A proper acknowledgement is generated at the sender side that message has been received at the other end. Okay, so this is the synchronous send. Asynchronous or the buffered send, it is what only known when the message has left. That means in this case, just it is telling you your message is sent. Okay, your message is sent. So the message will be go to the next point. Okay, so now here this is a box. These are not having any capability to tell whether the things has been accepted or not or received or not. So message will go through the communication channel. It will receive at this end, but there will be no acknowledgement. So meanwhile, while this message is transferring, this particular processor will perform the different task. Okay, he did not to be wait. He can go for perform some other important task which will be assigned at that instance. So this is the asynchronous and synchronous send. Now moving further, while doing this, there is some blocking operations. This is very important. They help you to block the certain operation till it is getting executed. So what are that? Some send or receive may block. Okay, may block until another process act. So block, whether to block or whether to not block, according to that we are having a different methods. So what is that? Some synchronous send operation blocks until receive is issued. Okay, that is the meaning of block. They will not allow to perform other things. They will keep on waiting. Okay, they will keep on waiting. What is happened for the message that has been sent. So synchronous send operation blocks until the receive is issued. Receive operation blocks until message is sent. So it is vice versa. There is a send and there is a receive. So receive will be there at the receiver end. What it will do? It will receive the message and then it will deliver the acknowledgement that okay, whatever the message that has been sent, it is received. Moreover, blocking subroutine returns only when the operation has completed. Okay, so when it is a blocking receive or blocking send, you will get an acknowledgement or you will get a message once that message is complete. So till that time, the process will not do anything. It is wait, that's all. And once the operation is complete, it will start executing some other work. So now we want to see what is a non-blocking. So in non-blocking, what it does, it is not blocking anything, just it is helping you to do some additional work as well. So non-blocking operation returns immediately. Okay, returns immediately and allow the subprogram to perform other operations. Okay, so take a simple example. This is the processor. It is sending the message. This message will reach to this point. So now while sending, it will move through the communication channel. Meanwhile, this processor can do some another work. Okay, can do some another work. That is the use of non-blocking. So we have to be very careful while using blocking and non-blocking. So whether that send need to be have an acknowledgement, that you have to decide. If you require an acknowledgement, so it will be blocking. If you don't require an acknowledgement, in that case it is a non-blocking, where you will get a message or you may not get a message in non-blocking. Okay. So meanwhile something was going here and then at last you will get a beep. Yes, the message was sent. Fine. So that is only the difference. The difference is in the middle where the message is getting transferred. At that time, you will get the chance to perform some other work. Now then there is another communication. So first we have seen point to point. Next one is a collective communication. So collective communication routine are higher level routines. That means what it does? It collects the data from so many sources. and it analyze that data, perform some operation and generate the result. That is exactly called as a collective communication, where all the processors are involved. Collective communication means whatever the number of processors are there, they are involved in that particular computation. So several processes are involved at a time, that already I have told, may allow optimized internal implementation, that is a tree-based algorithm. So the implementation is totally dependent upon the user. You can use a tree-based implementation, you can have a maze-based implementation, and you can have any other way of implementation where some little bit optimization will be there in terms of involvement of processors to solve the problem. So we'll see this in detail. So in collective communication, the first category which we want to see it is a broadcast, sending the message one to many. Okay, so one is the sender and many are the receivers. So just the processor will send the message and everyone will going to receive as it is. That is the broadcast. Now in the broadcast, let's say another example is a reduction operation. So reduction operation, what it says that now there are number of processes. One process will going to start the operation. That means it will going to send the data to the different processors, and it will also keep some data for the processing. And once the result will come from other processes, it will just going to combine. That is exactly a reduction operation. This is one of the important operation where just by specifying reduction operation, these processes will start performing their independent task. They will generate their own result and that result sent back to the main process. So what it says that combine data from several processes to produce a single result. So suppose this is your master and these are the slaves. So what master is doing? Master is sending the program to all. Same in the same, master will send the data. Okay, some data to this processor by seeing the capability, some data to this processor by seeing the capability likewise. And then these different processes will perform their task and they will send the result. So now in this example, what we are doing? We are trying to find out the sum of vector elements. So some vector elements will be done by this, some of the other elements will be done by this. So these are the local sum. Okay, this local sum will be sent to the master. What master will do? It will combine the data which has been received from different slaves, and it will go to give the final sum, which is called as a global sum or the sum of array elements. Okay. Now moving further, there is another concept which is called as a synchronization, which is termed as barriers. We have to have the barriers because we are having so many processes. Yes. So when so many processes are there, so these processes need to execute in a sync. They have to have some kind of synchronization. So to allow that synchronization in OpenMPI, we can apply the barriers. Okay, so barrier means a particular point where all the processes will come and they will stop, and once all the processes reach to that stoppage, then they can go further. Okay, so see here the one process who have executed very fastly, so it is reaching to the barrier. Now it has stopped over here. Then another process, they have also finished, they are also running towards to do something else, but there is a barrier, so they all will come. They will record their attendance here, they will record their entry here, and once all the processes that has been created by the program, so let's say the processes created by the program was 3, fine, so 3 will be get recorded at this point. If 3 are reported here, then these 3 processes are allowed to go further to perform the computation. So see what happens. From here to here, you are having some parallel computation. Okay, from here to here, there is some parallel computation. This parallel computation will be executed by 3 processes. Okay, so it is possible that some process may finish the work fast, so it will come at the barrier. See, moreover, all other process has to come. So 3 processes, if they visit here, so this barrier will be open. Then from this point onwards, it is possible that you may have another parallel user. So they will once again start to execute some program, and they will also come to a particular aim where the similar kind of barrier will be available. So there also they will stop and then further they will go. So this is the way synchronization can be achieved, because synchronization is the major concern. Fine. So if you are allowing the process just to go further, so we are not able to synchronize, and even we are not able to see the consistency in the data. So now these are the different concepts that we require. Now we move towards the format of MPI program. In what way you can write down the MPI program? So the first and important thing that we want to see here, MPI routine is defined, which is a language independent. Okay, there is no barrier of language. Okay, any language will support MPI, that's all. And your MPI command will start with MPI underscore and then name of the function. Okay, whatever the job. So MPI underscore, it is the namespace reserved for MPI constant. Your variable name cannot start with MPI underscore. Yes. So in that way, now this is the way the program is written. And most of the time, means always, not most of the time, always, your program will have this structure. So the structure is what? The MPI initialization we have to do. Okay. So here we have to pass the particular arguments that we will see later. So the first stage is initialize the MPI environment. So by using this method. So it will initialize the environment. Then here what we are doing, we want to print, we want to specify the number of processes. That is, how many processes will be there. Okay. So what we will do? We will call this method MPI communication size. So that communication size means how many processes will be there to solve the job. Fine. So that can be MPI communication world, this variable will be there, and here it will have the size. So 7 processes, 4 processes, and that particular processes will be the part of MPI communication world. Then we have to assign the rank to each and every processes. So for that MPI communication rank we have to call. So that will be in the MPI communication world only. All the process lies in this, and each and every process will have some rank which will be start from 0 to n-1. Once this is done, here you have to do the task. Okay, here you have to do the task, that what master will do, what slave will do, and what all others. So that parallel code can be written over here. Okay, and once your code is over, after that we have to finalize. That means we have to close, we have to destroy that communication world, so that that should not get continue further. So initialization, finding the size, that means deciding the size of the communication world, deciding the communication rank, then the number of core work which we have to do, and at last this is. So this is the format all the time we have to follow. Only this is the change. Here only you have to change. And the same program will get replicated for number of processes. Okay, same program will replicate it for number of processes when they will go to perform some task. So moving further, how that MPI initialization is. So MPI initialization, it requires some variables. So most of the time this variable will be the command line argument. So you pass some data from command line argument. Based on that, MPI initialization will take place. Okay. So must be the first routine. It has to be the first routine. Okay. It has to be the first routine in the program. Then communicator. We require a communicator, because without communicator it is not possible to have the communication. So the communicator is what? This MPI communication world. The infrastructure has to be created. So all processes of MPI program are the member of default communicator, which is MPI communication world. So once this is established, all the process can easily communicate. Okay, and this is available in this MPI.h, so which is already there. So just you have to utilize this variable. That's all, nothing else. Moreover, each process has its own rank in the communication. So this is your communication world. Inside that communication world, you will have the processes, and each processes will have their rank. Okay, and these ranks will start from 0 to size -1. Size means the size of communication world. So here the size of communication world is A. It is 7. So this is 7 minus the size like 1, 2, 3, 4, 5, 6, 7. So 7, so that is from 0 to 6. That way the ranks will be there. And through this ID 1, 0, 3, 5, you can communicate with each other. Okay. Now the rank. So already we have seen, but still we have to see. So the rank we have to call. So rank will be the identifier for each and every communicator, for each and every processes which are the part of communicator. Okay, and this rank is one of the basis by which we can distribute the work and we can distribute the data. Okay, so without calling this method, it is not possible to distribute the work and distribute the data. So that simply is getting called MPI communication. This is the communication variable and the rank. So that we can easily see this all processors are having their own rank through which we can communicate with each other. Now then size, that we have already seen in that program. So size is also we have to specify. So size will going to be determined. So by default, whatever will be the infrastructure available, that it will be take. Otherwise, we have to specify that these many processes are there and they will be the part of communicator. Okay. So just by calling this method, you can specify the size. So there are 7 processes, there are 8 processes, there are 9 processes likewise. And at last, MPI finalize. So MPI finalize, what will be done? Must be called at the last. You have to call this last. That means when you feel that all your open MPI work is over, so last you have to call so that you can finish that entire MPI communication infrastructure. And moreover, after MPI finalize, you cannot call MPI calls. After that, it is not allowed. Like in OpenMP, we can have different parallel reason. Okay, one parallel reason, then after that another parallel reason, and then another. But in OpenMP, it is not like this. Whatever the job which you have to do, that you have to finish before the MPI finalize. So MPI calls are forbidden. Especially reinitialization of MPI INET is foreign. You cannot reinitialize the MPI communication word. Whatever you want to do, you just identify and that you have to put in between MPI initialize and MPI finalize. That's all. So this is the example which you will see what is the output for this particular program. So here, a simple program, once again, here we want to print the processor name, the processor on which I am working, and I want to print the different processes. They are printing the name of the processor. Okay. So simple program, I am having a command line arguments argc, argv. Then I am, so in this program I am not passing anything. So that's why initialization null. No argument at all is passed over here. Then communication world size I have to specify. So MPI communication size, this method is getting called. Fine. Then get the rank of the process. So world rank is the variable, just that we have to pass. So communication rank will be get decided with this. And then here, this is the processor name, which is one of the predefined variable where MPI max processor max name, this is also predefined variable. So this particular array, which is a character array, will going to have the name of the processor on which I am working. And then I am using one integer variable which is a name length. It will going to print the length of the processor, the length of the name. Fine. So MPI get processor name, this is inbuilt method. So by calling this, by supplying this array and this particular variable, it will going to tell you what is the name of the processor. Fine. And then we are printing this message, hello world from processor, then a rank of the processor, and out of the number of processes. Okay. So processor name will be printed, rank will be printed, and size. So world size means the number of processors or processes involved in the communication world to print this message. So suppose you are having 4 processes. So this message will get printed by 4 processes. And at last, we have to finalize MPI environment. So MPI underscore finalize we have to call at last. So we'll see the output. So once you will run, the output may come like this. So to get this output, what you have to do, you have to specify 4 processes. dash NP space 4 you have to specify, and the name of the processor is status. Okay, that is 1, 2, 3 is get printed. So different processors. And how many processors are there? Total 4 processors. And these are the rank of the processors out of this 4. Fine. So this is the way NPI program can be written. Now after that we should know what are the different data types supported. So in the right hand side you can see the data types that are available in C program, and corresponding to that the data types that are available in MPI. So MPI underscore I, it is the prefix, you will see always. So this is a char, short. Why we require this? We require this when we send the message. So what is the data type of the message, and moreover what will be the size of the message. So for that this is very important. Now moving further, now coming to the example of point-to-point communication. How that point-to-point communication takes place. So communication between two processes, that is fine. Source process send message to destination. So suppose this is your source, this is your destination, it will send. So at this end you will use a send message, send method, and at this end you will going to use receive method. And this everything will be in MPI communication world. So processes are identified by their rank in the communicator. So already processes are there, so easily I can target a source and I can target a destination, and through that I can send the message. So how that particular method is, because in the method I have to specify so many things. So MPI send is the first method which will be utilized here. So here we have to specify some buffer size, okay, how much buffer that can be required to store that particular data. Then the count, okay, so count of the bytes. Then MPI data type, that is a data type just we have seen, whether it is integer, float, real, whatever it may be. Then destination, so destination is either process number 4, process number 6. Then there is a tag, okay, this tag is related to this send. So this tag will be common with respect to receive also. And then we have to specify MPI communicator. So this is the format. So similar kind of methods are there in the MPI. So just this method you have to call, and the program that you want to execute, that you want the different processor can execute, that you have to specify, that's all, nothing else. Not much programming is required at this point. Okay, so what is buffer? Is the starting point of the message, at what point that message with count element, how many elements are there, which describe the data types here. Destination, the rank has to be specified in the communication world. And tag is an additional field which is non-negative integer, which is just for a piggyback information. That means corresponding to this tag, whether send as successful, corresponding to this tag, whether receive is successful or not. The tag can be used by the programmer to distinguish different types of messages, that's all. So I say tag is 1 for receive, so I have to use a tag is 1 for send also. So that will help me what kind of messages that I am exchanging. Then there is a receive method. So MPI underscore receive. So in the receive, what are the buffer? Okay, the buffer in which the data need to be get accommodated, the count, how much bytes, then the data type, then the source, from which source that has been oriented, and the tag. So this tag will be same as the tag which was specified by the source. Then communicator, and then the status. So this MPI status will going to tell whether the receive is successful or not. So buffer, count, data type already we have seen in the previous slide. Receiving messages must be with the communicator, and then there is a one envelope information to return in the status. So the status will have certain information which is telling whether there is a kind of error or not. Fine. And whatever the output arguments, this is your output argument and this is your output argument, they are represented by this particular color. Only messages with matching tags are received. If tags are not matching, the message send and message receive will not going to take place. Because the send is initiated first, then receive will be there. If receives tag is not matching with the send tag, so the message exchange will not going to take place. Okay, So these are the different things that we have seen. Now we are going to see the programs. Okay, there are so many things that are there, that communication mode, then communication mode with respect to synchronous, asynchronous, and receive, and what they do. Okay, so these are there. Then ping pong operation is there, non-blocking communication. Then this is the example. So now we are going to move to the programs so that you can get an idea in what way the program is written. Okay. So I stop at this point for the theoretical part. If you are having any doubt, you can ask me at this point. I will happy to answer. So any doubt with respect to these theoretical aspects which we have seen just now, so that we can move towards to see some programs. So any doubts regarding the theoretical aspects of OpenMPI? Okay, so now we will move further to see how the program can be written, how that can be executed, and you will going to see the results. So there are many programs that are available for the practice today. So first of all, we will see the first program, which is MPI Hello World. Okay, so that just we can get a feel and we can get an easiness to write the program. So the program is just what we are doing. We want to print a hello world and we want to print who has claimed that particular message. Fine. So what we are doing, just we have some variable we have specified here. The first method, which is MPI initialize, that we have done. Then communication size we have specified. Then communication rank we have specified. And then here what we are doing, we want to get what is the processor name. So this is the program in which we are going to print the processor name by the different processors. Okay. And now this is the particular task. This is hello from task. This is get printed by all the processors. And this is the particular task getting printed only by master. And what is the ID of master? ID of master is 0. So this will print one time and this will print many times based on the number of processes. Fine. So simple program. So we will go first of all on the terminal. We will see. So once you will going to install OpenMPI on your machine. Okay. Once you will install OpenMPI on your machine, what you have to do, you have to check whether it is installed or not. Because sometimes it may be possible that you are installed, but it will not be able to get installed, and you feel that I have done the installation and why I am not able to use it. So to check, this is the command you have to check. So what we have to check? We have to check for MPI CC, that is MPI compiler, and we have to see MPI run, that is which will going to run the program. So for that, just you type this command on your terminal and you can see whether it is available or not. So MPICC -- version. So if you type this, if you get this message, okay, if you get this message, means MPICC is available on your machine. Okay, MPICC is available on your machine. Let's say it is not installed on your machine. Suppose the name is MPI. Suppose this is the MPI. If it is not installed, and if you type this and -- version, so it will say it is not available. Okay, it will say it is not available. So if anything is not installed on your machine, just you can check by that particular service name, whether it is a GCC or MPICC and -- version. So it will tell you that it is not available, you have to install. If it is available, an appropriate message will come and the version will going to get displayed. Fine. Now, so MPICC is available. Now then we have to check for MPI run is available or not. So MPI run -- version. So both are available. Okay. So we are having open MPI 4.0.5. So now this is the latest which is supported by my machine. Okay, and do not use the very latest. Just use below one. Just you see whether it is specifying that it is a stable version or not. Okay, just don't install the latest version, because the latest version is keep on evolving, it is keep on fixing the bugs. So try to always, with whatever the kind of software which you are using for your experimentation or for your research, always use one version lesser than that, because that version is a stable version. Fine. So now I am having MPI-CC and I am having MPI version, MPI run both available. Fine. Fine. So now we can run the program over here. So whatever the program which we have seen, that we will run. Already I am in that particular directory. I need not to move anywhere. So I will see the program. So these are the different programs that are available at this point. So what is the first command? MPI-CC. I have to compile it. The name of the program is one_MPI helloworld.c. Okay, and then I am creating an object file exp1. Okay, so there is no error in the program. Now I have to run the program. MPI run. So this is one -np. NP stands for number of processes. Then suppose I want to create 4 processes. Okay, and then the executable. So what is the executable? This exp1. So /exp1. Okay, so now in this case what it is giving me? It is giving me some error. So this error I am getting from yesterday only. So before to that my machine was working. Okay, so what it is happening? It is not allowing me to access the number of processors that are that are there on my machine. Okay, it is not allowing me at this instance. So I think some problem is there, because I am using the machine in dual boot. Okay, and that to be unsecured mode. Okay, I am using in unsecured mode, so that's why it is not allowing me to access all other processes. Okay, but the same program we can run by using single processor. Okay, so I'll show you that. So this was your executable. Okay, what output we are expecting? The output we are expecting hello from task, that is here, whatever the task, and then the name of the processor is required here, and then this is the message will get printed by the master. This has to get printed by number of processors. Okay, but in this case, now due to the problem in the software, and it is not allowing me to access the number of processors. Okay, so this particular message will get printed only by one processor. So that we will see. So I'll run it. So see, we got the result. So hello from task 0, that is the master thread. On means this is the processor, this is the name of my processor, my machine name. This is the name of my machine. User HP ProBook 440-G6, and then master has to print this particular message. So number of MPI task is 1. Okay. So still we are able to run with one particular process, or we can say one thread. Fine. So that this what later on can be fixed, but still we are able to get a result. It is not like this that we are not getting a result, we are getting a result, but everything will be done by only one processor. Okay, everything will be done by only one processor. Now moving to, so same thing will happen for the next program as well. We are not able to see that we have seen in the OpenMP. Yes, in OpenMP we have seen that the number of processes are involved and they are printing their own statements. Fine, but in this case we are facing some problem. are moving for the other programs. Okay. So now this program, I will going to explain what exactly we have done and what are the functionalities that are available. Fine. So next program we will go to MPI, where we will going to use the blocking send, because we have seen, because the OpenMPI having so many concepts, so all are not able to cover in that 1.5 hour, but the program will try to understand how that blocking send is utilized over here. Fine. So the program is simple hello program that uses blocking send or receive. So blocking send or receive, what it does not allow, means it waits for that particular operation to get finished. Okay. Once the operation is finished, okay, then it will go for another operation. So see the program. So we are having a number of tasks, task ID, length, the host name we will going to print, that is the name of my processor, okay, or my machine. Now MPI initialization is the first method that we are calling. We will going to pass some argument, command line argument. Then is the communication size that we are specifying. Then rank we are specifying, and here we are calling MPI get processor name with host name and length. So that is what we have done in the previous. Now here this is the message will get printed by all the hosts, all the processors available. Then this is the task which will be done by only master. It will going to print how many tasks are there. Now here see what we have done. So partner, and then send and receive with the partner. So determining the partner and send and receive with respect to the partner. So see what this code says that. So we are having a task ID. What is this task ID? The ID of the processors. Okay. This is the rank. So if rank is less than number of tasks divided by 2. So let's say number of tasks is 4. Okay. So 4 divided by 2, what it is? 2. That means it is applicable for 0 and 1. Okay. This is applicable for 0 and 1, and this is applicable for 2 and 3. Okay. This is applicable for 2 and 3. Yes. More than that, if they are more than that. So if 4 are there, so 0 and 1 will do this, and 2 and 3 will do this. So what it is? Partner is equals to number of tasks divided by 2 plus task ID will be done. Then message will be sent with the task ID. So what is the task ID? It can be 0 and it can be 1. So then what we have to send here, we have to send the count. Okay, so only 1 byte we are sending. Fine. Then it is the integer type. Then the partner to whom it has to get sent. Okay. And then the number of this is, I think this is the buffer size here, and this is the number of bytes, and then communication vault. Then receive. So send will be done and the receive will be done. So whatever the message that has been sent, which is with the particular address, which we have specified here itself, which is integer, then this integer data type, then the partner which will be calculated from here, then this one that is the count of the integer, the communication vault, and the set, that is the status, whether it is a failure or if any errors are there. Similar kind of things we have done here also. So here what we are doing, TID -1, this way partner IDs get created and the message and the task are get sent. So here there are some sender and there are some receiver. So who is the sender? Sender is 0 and 1 and the receiver is 2 and 3. Okay. And at last the tasks in the partner, they are getting printed with respect to task ID and message, and at last it is finalized. So let's see, I try to run this, what happens. We will see, though there are the problem. So MPICC program number 2 underscore dash O EXP2. Now I will try to run it. So MPI run is not running in this case. MPI run dash NP4, if I go, it is not helping me to give the result. It is giving the segmentation fault, but we will try to run this. Okay, so we got a message, but there is only one process, so there will be no blocking and non-blocking kind of communication. But we got the message, hello world from task 0 on user HP Pro. Okay, and then master number of MPI tasks are 1. And in this case, we are not asking anything to enter. Yes, we are not asking anything to enter. But here state is waiting to perform because it is a blocking. Okay, see here it is waiting because it is a blocking send. So sending we have done, but receiving acknowledgement will not come because there is only one process. Okay, there is only one process. So that process is waiting for the acknowledgement, but in this case you will not get the acknowledgement because we are having only one process. So I will do break here, Control Z. Fine. Now moving towards the next example, that is, let's say, non-blocking send. Okay. So in non-blocking send, what will happen? It will send and it can do some another work. In what way that is written? So here determine the partner and then send and receive. So non-blocking, it is written by I. Blocking, it will written by, just you will see, blocking it will be written with send only. Send and receive, they are blocking, and without that it is non-blocking. That is I. So it will receive, okay, and it will send. So receive is there at the other end and send will be at the other end. So we will try to run this program. Let's hope we will get some result over here. So MPI CC third program -O EXP3. Okay, it is executed. EXP3. Okay, so what happens over here? We got the first message and for, so we are not able to determine what are the processes. Yeah, so that's why we are getting an error. So if your OpenMPI properly installed with all the configurations, you will not going to get this message at all. So this was the what was non-blocking send. So just this is the method we have to use. Specify all the parameters which are required, and then your work is done. Okay, and here at last, here it is MPI wait with respect to whatever that has been requested and whatever the status at this point. Okay, now moving further, the fourth one, which is a ping pong, that is a blocking, send and receive. Blocking, send and receive. So we will see in the code what it is there. So see, what we have done in the code, the master will do this task. Okay, the rank 1 will do this task. Okay, and if rank is less than 2, they will going to do this task. So we have divided that what are the particular processes what they will going to do. So if number of tasks are greater than 2, so it will print this message, the destination is 1, source is 1. Okay, destination is 1, source is 1, and then here we are using blocking send and blocking receive. So what we are sending some message, output message, which is V message we are sending. See here V, and then that see it is only one character. It is of character type, destination, then tag we have to specify, and then at the other end it will going to receive. Okay, so receiver will be the source and destination will be the 1. Okay, then rank is 1, so rank 1 what it will do? That is, it will receive from the destination. So first of all receive is there and then there is a send. Rank 0, first of all it is the send and then there is the receive. And if rank is less than that, that means they will not going to take part. So it is a ping pong, sending to one process and receiving from that process. That's why, so this will go into ping and this will go into pong. That means it will acknowledgement that the message has been received. And when the processes are less than 2, so this messages is get printed at the last. So let's see what output come for this. It is a program number 4. -O EXP4. It is executed. There is no problem in the program. EXP4. So now in this case, it is not able to identify the processes. So that's why it is saying that error in the MPI send, and then we are not getting the rank. Then it is not able to identify how many processes are there, and hence everything is get aborted. So I try once again. I am not able to recognize what from these errors are coming. Okay, so the processes are not there. That's why, because one process has to send the data to another process. That is the logic we have adopted in the code. So likewise, there are so many programs which I am going to share with you so that you can practice on that program. We will see one program which is this MPI array. Okay, MPI array. So I'll read out the description and what way that has been done, that you will see. So this program demonstrates a simple data decomposition. So what the data will get decomposed to number of processes. So this is one of the important tasks. The master task first initialize an array and then distribute the equal portion that array to the other task. After other tasks receive their portion of the array, they perform the addition operation to each array. So it is the addition of array elements. So master will divide the data into equal chunks sent to the respective processes. The master task does likewise with its portion of the array. As each of the non-master tasks finishes, they send their updated portion of array to the master. An MPI collective communication call is used to collect the sum maintained. Finally, the master will going to find out the overall sum. So see how that can be done over here. Okay, so we'll directly jump to on that particular part where this has been done. So here, so we are having some array size, and that array size is get divided by number of tasks. So suppose there are 4 tasks and you are having 1024, you are having 100 element in the array. So 100 divided by 4, it is a 25, 25, 25. So 25, 25, 25 will be given to the each processes. Okay, if task ID is equals to master, so what we have decided, master will going to initialize the array. Okay, and master will going to perform some sort of addition of its own what we can say array, and then master will going to send the data to other processes. So that is done here. So task ID is equals to master, so master is initializing, data is equals to I plus 100, and here master is computing sum is equals to sum of that particular data. Okay, here it is calculated sum. Now see after that. So array sum is equals to sum at this particular point. Now we are setting the offset, which is a chunk, because after that point that data need to be go to another process. So first 25 will go to first process, second 25 will go to next process. Okay, so for that we have deciding the offset. So destination is 1. Okay, so first of all it will go to rank 1 process, then it will go to rank 2 process, then it will go to rank 3 process. So destination equals to 1, destination less than number of tasks, destination plus. What we are going to send. So what is that offset? So these many values that we have to send. Okay, then 1, we are making a tag at 1 over here. That is the starting position, a starting position at this point. Then it is the integer data type. Then the destination point, which is 1. Then the tag for that particular send, and then communication word. Okay, then there will be an MPI send. So this MPI send will be from the destination point. Okay, so data set offset, the chunk size, it is MPI float, and then destination. Okay, so yeah, fine. Then tag 2 and then communication word. So here it is going to print what is the element that has been sent, the chunk size, destination, and offset. And then offset is getting incremented by the chunk size. So next 25 will be going to the destination 2 likewise. Then what master is doing? Master will make a offset is equals to 0 because all the data transfer is done at this particular point. Then what my sum is getting calculated with respect to the method called as update. So update method will help you to find out the sum. Okay. So just you have to pass the variable offset, chunk size, and task ID. And here wait to receive result at each task. So whatever the processes are there, they will keep on receiving. So that will start from task I is equals to 1 till task ID I plus plus. So all the processes will receive offset, okay, the starting position, the data type, the source from where it has been started, the tag, then communication word, then status, then once again receive with respect to the entire data, chunk size, it is a floating point from the particular source, then tag, then communication word, and the status. So here all the processes will receive. Then we are making use of one procedure which is called as a MPI underscore reduce. So MPI underscore reduce, what it will do, whatever the output that has been generated, okay, based on this particular variable and some variable, it will combine and it will going to be the final result. So MPI sum, and this is a sum, it is of 1 byte only, MPI float, MPI sum, this is the operation name MPI sum that has to be done by the master under the communication environment. Okay, and at last, whatever this is for printing that particular offset, and so there is a how many output that is get printed. So if there are 4 processes, 4 outputs are get printed with respect to 4 processes. And if task ID is greater than master, so they have to receive, they have to perform the communication, and they have to send the data, and they have to reduce that particular data. So this is the way that MPI communication has to be there, and this is the method which we are going to update all other things. Fine. So at this point I stop. If any doubts are there, you can ask me those doubts. So any doubts you can ask. So any doubts, any queries are there, so you can ask.
Hello?
Yes.
Yeah.
Sorry, I'm not getting your voice clearly. Yeah, there is a question, can we send bunch of data from one rank to another rank at a time? Yes, you can send it, there is no problem. Because these two ranks are totally independent, yes. So just whatever the code I have demonstrated, just you have to specify that this particular rank has to receive and this particular rank has to send. So in that way you can do it.
I have another query.
Yeah.
Implement meta-analytic algorithms in OpenMPI. Available for that.
Which kind of algorithm are you talking?
Sir, like swarm intelligence algorithms.
Yeah, just what you have to do, you have to see what kind of task that is not dependent. Okay, because the parallelization, the first thing is your code should not be dependent. If it is a dependent, so whatever may be the programming language, it will not help you. So you have to see what are the independent tasks are there, and on that you can definitely use whether it is OpenMP, MPI or any other programming language. So you have to investigate that particular algorithm. You have to see what are the chances of what are that particular portion where you are not having much dependency. Or by applying the dependency analysis concept, can you resolve the dependency? If it is possible, then that code can be parallelized by using OpenMP and MPI or CUDA as well. Okay.
So any other participant have a question, please ask. Okay, sir. Thank you so much for a nice wonderful session.
Okay, thanks to all.
Thank you, sir. Thank you very much.
Yeah, okay, fine.